The mathematical concept of exact differentials is intimately linked to state functions, so it's important that we understand the properties of exact differentials before we move on. It turns out that any state function will have an exact differential. A differential is simply a small change in a property of the system. So if we look at the energy over time as we cool a sample by putting it into ice water, we can see that the energy decreases as a function of time. The total change in energy from our initial state to our final state is always designated as delta E. And delta E for a state function is simply the final value of the property, energy in this case, minus the initial value. This total change in energy is made up of a lot of little incremental changes in the energy. And if I want to talk about the instantaneous change in energy as a function of time, I need to use this incremental change or the differential of the energy. A state function, such as the energy, is typically a function of one or more variables. In this case, the energy is typically a function of temperature, volume, and number of moles. But if we have a closed system, we don't need to worry about the number of moles. So to simplify, let's think about energy, internal energy, as being a function of temperature and volume. When I have a state function, the total change in that state function, small incremental change, will be due to any changes in that function with one of the variables, say temperature, when I keep the other variable constant, say volume, times how much I've changed the temperature. But that only tells me about how the energy changes as a function of temperature. It doesn't tell me how it's changing as a function of volume. So I need to add the effect of changing the volume at constant temperature times how much the volume has changed. Any state function will have an exact differential, and the total change in any exact differential is the sum of the changes due to each of the variables. Notice that we've used partial derivatives to talk about the change with respect to each of the variables. This is because the change with respect to temperature tells only part of the story of the entire change in the energy, and we need to include the change with respect to the volume in order to get the full picture of how the energy has changed. Therefore, we have partial derivatives to tell us about part of the change in the total change in the energy. Another property of exact differentials is that their mixed second-order partials are equal. What do I mean by that? What I mean is that if I take the second derivative of the energy, I have the choice of taking, after I've taken the first derivative with respect to temperature, I have the choice of taking the second derivative with respect to volume or with respect to temperature again. Likewise, once I've taken the derivative of the energy with respect to volume, I have the choice of taking the second derivative with respect to temperature or with respect to volume. So there are 4 second derivatives possible. 2 of these derivatives keep the same variable that we're taking the derivative with respect to. So either I take the first derivative with respect to temperature and then take the derivative with respect to temperature again, all at constant volume, or do that with respect to volume, all at constant temperature. But the other 2 are mixed second partials because the first derivative is taken with respect to temperature at constant volume, and then the second is taken with respect to volume at constant temperature. For an exact differential, the order of differentiation does not matter. I can take it with respect to volume first and then temperature, and that will be equal to taking the derivative with respect to temperature and then with respect to volume. This is going to come in very handy because it's going to allow us to determine a number of useful expressions.